Hang on a second, the screen looks really small. Let's see if I can change that.
I think you could zoom in, Miss Martin, and it'll zoom in on ours.
It's like my screen sharing box that is really small, and I think that's what it is. Hang on a second, the screen looks really small. Wait, now I hear myself. What? Let's see if I can change that. Okay. I'm trying to make this screen bigger and it's not. Oh, no, I'm making it. Okay, I think it's just gonna have to stay like this because I can't. Oh, I figured it out. It's a double click. Okay, cool. Sorry guys, it's a learning process. Okay, now that that's figured out, we can get started because I think that should make it fit the screen better. I figured, yeah, okay. that was my voice again. All right, let's get started because it seems that this is working. Oh, there you go. I made it big. Okay, so growth and decay is the name of the topic today. And we kind of started out discussing coronavirus. And remember, we did that COVID-19 worksheet where you had to come up with the exponential equations that represented the change in people who are infected. And so we're going to be kind of going through a process that allows us to find those equations given a rate of change. So we're going to go through and kind of understand it, and then we'll come back to kind of full circle how it all connects with the COVID-19 kind of equations and how scientists have been using these kind of techniques that we're going to go over today. And we already went over part of this on our last class session when we talked about separation of variables. So if you can recall, we use separation of variables when we have more than one variable. So this first little question here, zoom in here. When is it useful to use the separation of variables? It's when we have two different variables. So sometimes we say both x and y, but because those are often the variables that we use, but it's not always the case, right? We can use any kind of variables we want. So I'll just say we have two different variables as part of a rate. Okay. So for example here, we have y prime is equal to 2x divided by y. So y prime means that this equation on this side represents a rate because y prime is a rate of change. And so what I like to do is change the notation. Y prime is the same thing as dy over dx because we see the function here 2x over y. X and y are both of our variables. If it's y prime, that means it's the change in y, and then it's going to be divided by the change in x. So this equation here, I can rewrite it as dy over dx is equal to 2x over y. And so this is a rate of change. It's the change in y over the change in x. But the problem is asking us to solve the differential equation. So when it's saying to solve the differential equation, what it means is solve for its original equation. So we're given the rate, we want to know what is the original equation, or in this case, what is the equation of y, because that's what we're changing there, dy over dx. So what is y equal to? What is that equation? So in order to do that, when you have a derivative, you want to find the original equation. To go backwards, we take the integral. But how do we take the integral of a function 2x divided by y when we have two different variables? We have to separate those variables. So I have dy on the left side. I'm going to need to move this y over to that side as well. So to do that, I'm going to multiply by y. And then the dx, I'm going to multiply that to the other side. So then I have y dy is equal to 2x dx. So there's the separation, and now we can integrate now that it's separated. And so the integral of y is 1/2 y squared. And that's going to equal the integral of 2x, which will be x squared. Since the 2 times the 1/2 will just cancel out to 1. So we have 1/2 y squared is equal to x squared plus c. Remember that constant, it just represents some number. So it's really the combined constants. So that's why I didn't write a plus c on the side where it's 1/2 y squared. It's just all combined onto one side. So this is our general solution. It's general because we don't know what c is. I'm going to go ahead and take it one step further and try and just isolate the y a little bit further. So the 1/2 in front of it, I'm just going to multiply everything by 2. So this whole thing gets multiplied by 2. That way I just get rid of that coefficient, and it's just y squared is equal to 2x squared plus c. You don't necessarily have to do it. It just kind of depends on if there's a next step to the problem. So like, for example, this problem, it just says solve the differential equation. You can just leave it like that. That's your general solution. There's going to be some cases later on where we're going to have to use that equation and, plug it into different things and do different things with it. So we would want to try and simplify it a little bit, like get rid of the fractions and get rid of, all those extras to make it easier to work with.
Miss Martin?
Yes.
You don't need to add, multiply the 2 to the c because it's just a number, right? It doesn't make a difference?
Exactly, yeah.
Oh, okay.
Right. As long as you multiply it to everything else, it'll still maintain that balance. So this, we can just go ahead and stop there. There's our general solution. We could take it a step further. I'm not going to write it out, but obviously if y is being squared, you can square root it. And so you'd have plus or minus square root of 2x squared plus c on the other side. At that point, we're almost overcomplicating it at that point. So I'm just going to stop there. Okay. So then this leads us to the next part. That was kind of like a little warm up reminding us how separation of variables works. And we're going to learn a theorem. And so this theorem applies to growth and decay of different rates. So in many applications, the rate of change of the variable y is directly proportional to the value of y. We're going to break that down in just a second. It says if y is a function of time t, the proportion can be written as follows. So this is the equation that can be written for that rate of change. So if this left side right here, dy over dt, that represents the rate of change of y. And I'm going to go ahead and write in a little bit more, because not only is it the rate of change of y, it's the rate of change of y with respect to t. So that is what represents the rate of change, and that rate of change is equal to k times y. So when we think mathematically, if we're like looking at different phrasing, if we look at this phrase right here, the rate of change of the variable y, that whole phrase is represented by dy over dt, that's represented by the equal sign. And then we see directly proportional. So whenever you see that phrase directly proportional, it's talking about proportionalities. So it's some number that's going to multiply to some other value. So that some number, we call it k. We use k to represent that. So if we look here, we have k times y. That means we have this value directly proportional to the value of y. So remember, we don't know what y is, but at this point we have a rate of change, and this rate of change is directly proportional to the value of y, whatever that is. And so you can see kind of the breakdown here. This equal sign represents the is for our phrase, and then we have k times y. That's what we use when it is proportional. Proportional, directly proportional. Okay, same kind of phrasing. So what does that mean? It's kind of like maintaining the balance, right? So if you have some y value here, we don't know exactly what y is, but we know that the rate of change of that y is going to be directly proportional. So let's say the y is equal to 1, then the rate of change is going to be 1 times k. If y is equal to 3, then the rate of change is going to be 3 times k. So they're always going to be matching up. Like if y changes, then the rate of change of y is going to change accordingly because they're going to be directly proportional. Now k is representing how proportional it may be. Like for example, if k is equal to 2, that means whatever your y is, your rate of change is going to be double that y value. And then it's just going to kind of maintain as y changes, right? It's going to keep that proportion. So that's what this equation is representing. And so we are going to take this equation and we are going to find the general solution to it. So what y is actually equal to. And since this is a rate of change, we know how to take a rate of change and turn it into a y equation. We just went through the steps, right? And so before we go through those steps again for this new equation, we already know what the conclusion is going to be because of this theorem. It's going to be y is equal to c times e to the k times t. We're going to do the proof in just a second to prove that that's going to be your y value. But since we're going to prove it right now, now it's a theorem, you can just invoke it and use that theorem whenever. So if you ever have an equation for a rate where its y value is directly proportional to that rate, then you know y is going to equal c times e to the kt. You're not going to have to go through the steps that we're going to do right now to prove it. So we'll talk really quickly about those steps and go through them. And then after that, we're not going to have to do those steps. So we are starting with dy over dt is equal to k times y. So we're starting with a rate and that rate is directly proportional to the value of y. So we want to figure out what y is. Well, that means we have to integrate this derivative. Well, how do we integrate this derivative? When we have two different variables, we need to separate them. K is technically called a variable, but remember K represents a number. So it keeps that property of a number. So what I'm going to do is this y, I have dy on this side, so I'm going to get this y over to the other side, and the dt, I'm going to move that to the right side, and the k, I'm just going to leave it in place. So what I end up with, I have to divide by y, so I get 1 over y times dy, and then multiply by dt, so I get k times dt. So remember, k is just representing any number. So now that we've separated the variables, we can integrate. The integrate of 1 over y is ln absolute value of y. And the integral of k, the integral of any number, is the number times its variable of integration. So it's going to be k times t, since t is actually the variable of integration here. We have dt multiplying that k. So k times t, and then remember, we need to add a plus c. Okay. Any questions on that so far?
Can you explain like kind of what you just said about like why it's just k times t instead of like the like the 1/2 k squared or whatever?
Mm-hmm. So k is not your variable of integration because our variable is t, it's dt, right? So you want to treat k as a number, as any constant number. So if you were, for example, to integrate 3 dt, that would become 3t.
Oh, okay, I see.
All right, so that's the property that we're using of the different constants. So if it was the integral of t dt, then you would be able to do 1/2 t squared because it's the same variable of integration. Okay. So from here, since we haven't arrived to this specific y general equation yet. I mean, technically we have, but we need to rearrange this a little bit. So we're going to go ahead and do that. We need to solve for y. So to get rid of y, I need to take the inverse of it, which is e. So that whole thing kind of gets raised up. So we have e to the ln y, and that e and ln gets canceled out, leaving me with y is equal to e to the kt plus c, because that whole thing gets placed into the variable, exponent. And we're almost there. Now we have y by itself, but we need to kind of work on the other side and simplify it. So we actually did this in the notes before spring break. We did a similar example to this where we needed to simplify this a little bit more. So we have to use our properties of exponents. If we have addition inside of the exponent, we can break that down. It becomes multiplication of exponentials with the same base. So e to the kt times e to the c. It's kind of like saying if you have 2 to the 1 times 2 to the 3, that's the same thing as 2 to the 4th, right? So similar, or even if you need to, x times x cubed, right? X times x cubed is x to the 4th because you're just adding those powers. So as long as you have that same base, that property applies. So there we are. And remember, c is some constant. And so if we take e, which is a number raised by that constant, it's going to give us some other constant. So this whole thing right here gets replaced by c. And so this becomes y is equal to c times e to the kt. And that is our general solution. So that proves this theorem. We've shown how we can go from this y, which is a differentiable function of t, right? This y prime is equal to ky. We can go from that to y equal to c times e to the kt. So that means that y is an exponential function. When your rate of change is in this format, is directly proportional to the value of y, that means your y has to have been, or had to have been, an exponential function to begin with. And so you see the format here, e to the k times t. If your k value is a positive value, that means you have exponential growth, right? A positive value, your function is growing. If k is negative, that means you have exponential decay. So we're going to be looking at an example next where we determine what k is equal to and what c is equal to, because this is still just a general equation. It's not a particular solution for that y value, right? Because this is not any kind of y equation that I can graph, because I don't have any values here and here to be able to graph it, right? Remember, when you graph it, you need one input and one output. So your input is t, your output is y. C and k are numbers, and we need to figure out what those numbers are. And in order to do that, we need to be given some kind of conditions to begin with, some initial conditions. So we're going to do an example here. Let's read through it together. First, it says the rate of change of y is proportional to y. So we're going to break down this phrase and see how this is written as an equation. But let's just keep reading first. When t is equal to 0, y is equal to 2. When t is equal to 2, y is equal to 4. What is the value of y when t is equal to 3? So this is our question that we need to answer. Okay, but we're going to go through our steps to be able to get to that point where we can answer it, because the question, what is the value of y when t is equal to 3, that means all we would have to do is plug t into an equation and get your output of y, right? But the problem here is, what is the equation? What is that? Where am I going to plug in t? So we need to come up with that. They've given us here the rate of change of y is proportional to y. So that's the phrase that we kind of broke down in the beginning, and we wrote it as an equation. So we're going to do that again here. It says the rate of change of y. So that's y prime, right? The rate of change of y, which I can rewrite as dy over dt in this case, because I see here it's giving me some value of both y and t. So that's telling me my two variables. So the rate of change of y represents dy over dt. And dy over dt is, so that's equal to, proportional to y. So when I see proportional, I know that's k to y, so times y. So what that equation there is dy over dt is equal to k times y. Now this is all that we need. It's in the correct format because of the proportionality, that we know that this is going to give us y is equal to c times e to the k times t. That is the general solution, because we have the theorem that tells us so, and we literally just did the work to prove that. So we know that's true. All we have to do is just write it. So there's our y equation. So one step closer, because now, remember, we're trying to solve for y when t is equal to 3. So really all I would need to do is plug in, oops, wrong pencil here. All I need to do is plug in 3 for t. But the problem is I can't solve for y just yet because I still don't know what c and k is. So that's my next challenge that I need to overcome here. So remember, they gave us some initial conditions. T equal to 0 when y is equal, or when t is equal to 0, y is equal to 2. So that's an input and an output. When t is equal to 2, y is equal to 4. That's another input and output. So I'm going to start with this first one, 0 and 2. I get to plug that in. Y is equal to 2 and t is equal to 0. And what this does now, k times 0, that's just going to be 0 because anything times 0 is 0. E to the 0 is 1. So 1 times c, that just gives me c is equal to 2. Now we figured one of those out. We know that this c is equal to 2. So I'm going to go ahead and plug that in. We're one step closer. We still can't plug in that t value because we need to figure out what k is. But remember, we have another point. So let's plug that point in. That's going to be 4 equal to 2 times e to the 2t. And now t is the only variable. So all I have to do is solve for that t. I'll start by dividing by 2. So 2 is equal to e to the 2t. Then I can, in order to get rid of the e, take the ln of both sides. That gives me ln of 2 is equal to ln e to the 2t. So that cancels. I get ln of 2 is equal to 2t. Divide by 2. Oh, sorry. Where did I lose? This should be a k. I was testing you all, making sure you were following. We're supposed to be solving for k. I plugged 2 in for t. So k is equal to ln of 2 divided by 2. So that, and I have to say, k is often going to be some kind of ln divided by a number, just because of it's an exponential function with the e. So oftentimes that's going to be the solution there. It's not the prettiest solution, but it is what it is. We can take that and plug it into our k value here. So I'm going to, here, let me see how far I can take this. Y is equal to 2 times e to the ln 2 over 2 times t. So this is what we call the particular solution, because now we have the c and k values to give us an equation, which is actually what you see graphed right here. That's the y value. So you can see 2 times e to the ln 2 over 2 times t gives you an exponential growth, because k equal to ln 2 over 2 is a positive value. So it's a growth function. So there we go. There's our particular solution. Finally, now we can plug in that t value, t equal to 3, to be able to solve for y. And then from here on out, we could plug in whatever value for t we want and solve for y. So, but in this case, I'm going to plug in ln 2 over 2 times 3. This will just give me a 3/2 here times ln of 2. I'm going to show you how to take this a step further and simplify it as much as possible. because we see an E and we see the ln in the power of E. So we know that those should be able to cancel, but it can't cancel if you have that constant, the 3/2 in front. So what we can do is our log properties, say if you have the constant in front, you can kick it to the back. So this becomes e to the ln of 2 to the 3/2, and then e and ln cancels. So this will become 2, because we have that constant 2 in the front, times 2 to the 3/2. Remember, when you're multiplying, you add their powers, so it becomes 2 to the 5/2. Okay, so that would be your y value. If you plug it into your calculator, it's approximately 5.657. Okay. So that's our solution. That's the y value that corresponds with that t equal to 3 value. And if you look closer, sorry, let me zoom out so you can, if you need to take notes, but if you look closer into the graph, you'll see all of those points on there. You see 0, 2, that's the initial point there. You see 2, 4, that's this point right here. And then you see when t is equal to 3, notice how that y value is between, this is 4, this is 5, this is 6. That y value is right between 5 and 6. So approximately 5.657. So it lands perfectly along the graph, as it should, right? It should make sense. And that's our example there. And also that is time for class to end. Let me know if you have any quick questions right now. We're going to finish the rest of this up tomorrow in class, but and I'm going to stop this recording, but let me know if you have any questions. Otherwise, have a great day, everyone. I am going to post some practice problems for you to practice this evening. Shoot, how do I end this? Oh.